On the 23rd of November, 2023, scientists at LIGO detected a tiny subatomic signal, the final echo of a cataclysmic event. Somewhere, halfway across the cosmos, two black holes had collided with incredible force. This epic crash sent ripples through the universe, powerful enough to be picked up here on Earth, more than 7 billion light-years away. This isn't an unusual type of event for LIGO to detect, but what was unusual is that neither of the two black holes involved in the collision should even exist, according to our current models. They fall into the so-called mass gap, a range of black hole masses that, as far as we know, are impossible to create. Now scientists are trying to unpick this faint and unbelievably intricate signal, to learn how and why these epic space giants met, and solve one of the biggest mysteries in astronomy. Where did these impossible black holes come from? All across the cosmos, pairs of black holes are locked in a gravitational dance. Over billions of years their orbits gradually tighten, bringing them closer and closer, until finally, they collide. On impact, the two black holes merge, but in the process, something new is born, one, brand new, even more massive black hole. These epic collisions are intensely powerful, releasing many times the mass of our Sun in bursts of energy, but they are also some of the hardest events to detect, because black holes play by their own rules. They have a habit of trapping light and matter inside themselves, meaning they don't emit anything we can see or measure. Not yet anyway. If we want to hunt black hole collisions, we need to look at one of Einstein's last untested predictions for the theory of relativity. Einstein predicted that when something massive accelerates through the universe it should generate ripples in spacetime, that is, the very fabric of the universe itself. We call these ripples gravitational waves. Most of the time, these fluctuations would be far too small to measure, but, theoretically, something unbelievably massive, accelerating extraordinarily fast, could produce gravitational waves large enough to detect on Earth, just something like two black holes colliding. In the final death throes of their spiral, binary pairs of black holes approach the speed of light. And just as Einstein predicted, in the last few orbits before they merge, for just a fraction of a second, they create a blast of gravitational waves that can be incredibly powerful, rolling through spacetime in all directions. With each wave, spacetime itself contracts and expands, but, even for a black hole merger, the amount we detect is tiny, thousandths of the size of a proton. Einstein never saw his theory proved because the technology did not exist to make detections precise enough to measure these changes. In fact, he believed his theory was untestable. And, until 2015, it was. LIGO. Almost exactly 60 years after Einstein's death, scientists made their first direct observation of gravitational waves, with a truly revolutionary detector. This is the Laser Interferometer Gravitational Wave Observatory, or LIGO. You might remember it from my previous video which you can watch here, but essentially its job is to detect gravitational waves. LIGO consists of two detectors, spaced 3,000 kilometers apart. That's about a 3.5-hour flight on a plane, but a journey of less than 10,000ths of a second for a gravitational wave. At each base, a pair of 3.5-meter tall concrete pipes stretch at right angles into the distance. The pipes are so long, more than 4 kilometers each, that they have to be raised from the ground by a meter at each end, to keep them lying flat as Earth curves beneath them. At the end of each pipe sits a mirror. Each is 0.3 meters wide, weighing in at 40 kilograms, and polished to a perfect sphere with sub-nanometer precision. The mirrors are suspended by a system of pendulums made of fused silica fibers, insulating them from the slightest seismic tremor. By firing lasers down LIGO's detector arms, scientists can measure the exact distance between the two sets of mirrors. When a gravitational wave rolls through our planet, the rippling of spacetime it causes, which, by the way, is about 1,000th the size of a proton over this scale, creates a pattern in the reflected laser light that can be measured by LIGO's software. And with that, we can detect gravitational waves. Not only can we use this to spot cataclysmic events happening billions of light-years away, but by analyzing the signals scientists can calculate the scale of the event that has produced them, and paint a fairly detailed picture of what was involved. For 10 years now, LIGO and its collaborators, mainly the Virgo detector in Italy, and Kagra in Japan, have been detecting black hole collisions across the universe. The collaboration has seen over 300 mergers and revolutionized the field of black hole studies. In fact, in 2017, its founders won the Nobel Prize for Physics for proving the existence of Einstein's gravitational waves. In 2023, this observatory made yet another find that, once again, shocked astronomers. It was a signal scientists called GW231123, and what it showed was seemingly impossible. GW231123 lasted about 1/10 of a second but stood out clearly, a blip in the readings about 20 times louder than the typical detector noise. The signal was so strong that the team of scientists who were involved in the discovery might have written it off as an anomaly, until the same measurement came in from the second detector on the other side of the states. The team still had to check this wasn't a random blip. By simulating thousands of years' worth of fake data, they found that the probability of random noise mimicking GW231123 was less than once in 10,000 years. In other words, they were pretty sure it was real. So they set about working out what exactly it could be. The models that best explained the patterns they saw in the waveform of the signal were those of highly spinning black holes colliding, but even then the signal was quite unusual. It appeared to be just the second half of a black hole collision, what's known as the ring-down phase. As the new black hole formed, it rang like a dampening bell before settling down, and it was the gravitational waves released during this end portion of the merger that LIGO had detected. Taking into account all these irregularities, the team concluded that around 7 billion light-years away, two black holes had merged, in a powerful collision, to form one single black hole with a gargantuan mass somewhere between 182 and 251 times that of our Sun. This was a stunning discovery. Before this event, the most massive black hole ever seen after a merger had been about 140 solar masses. At the moment of the collision, it was easily the brightest event in the entire cosmos, emitting 15 solar masses of energy, that's nearly 3 quindecillion, or 3 followed by 48 zeros, joules. It would take the Sun about 200 trillion years to emit that much energy. It's more than what was produced by every single other star in the universe combined at that moment. And what's more, all that energy was released as gravitational waves, which spread out through the fabric of space-time, traveling billions of light-years, until eventually, they reached our planet. With further complex analysis of the signal, the scientists were also able to tease out information about the two individual black holes involved in the crash, and this is where things got strange. Based on Einstein's theory of relativity, theoretical physicists have built a huge library of theoretical waveform templates. Each one simulates the signal a different black hole binary would produce if heard by LIGO. For example, heavier black holes merge faster, creating a shorter, higher-pitched signal. Scientists compare each new signal to their vast catalogue of theoretical collisions, to see which is the best fit. It turned out that the two black holes that produced this titanic space event were 103 and 137 times the mass of the Sun, and spinning about 400,000 times faster than Earth, close to the speed of light. That's almost as fast as it is physically possible for them to go. And this revelation presented a huge mystery. Because until now, physicists did not believe that either of these black holes should be able to exist. In some ways, black holes are very simple. They are such pure and extreme phenomena that they can be defined by only three characteristics: spin, or angular momentum, mass, and electric charge. For many years, scientists have predicted a specific subset of black holes that should not exist. Specifically, black holes with masses roughly between 50 and 130 times that of our Sun. These are bigger than your average black hole, but not the supermassive monsters that live at the center of galaxies. This is called the mass gap, and to understand it, we have to look at how black holes typically form. When really large stars reach the end of their lives, and start forming iron in their core, they eventually collapse because there is not enough radiation pressure to prevent the outer layers from falling in under gravitational pressure. These stars then explode as Type II supernovae. If the original star is very massive, typically more than 20 to 30 times the Sun's mass, and the remnant core left after the supernova explosion exceeds the neutron star limit, which is around 2.2 to 3 solar masses, then it will keep collapsing, forming a black hole. But there are even more massive stars, giants, which formed in the very early universe, with between 130 and 250 solar masses. Some end in violent supernovae that tear the star apart completely, without leaving the superdense core behind that is required to form a black hole. Others, more specifically pulsating red giants, throw off layer after layer, reducing its mass. Then the final, much smaller, star would collapse into a neutron star or smaller black hole, again preventing the formation of an intermediate mass black hole. For almost 10 years, it seemed like our predictions were right, as gravitational wave detectors like the LIGO-Virgo-Kagra collaboration did not find any black holes of this intermediate size. Then, GW231123 turned up, and revealed two black holes merging, both within the mass gap. Our theory, at least in some cases, was wrong, and scientists have had to come up with a new hypothesis. One possibility is that they grew through a series of smaller black hole mergers, that the collision LIGO detected was just the latest in a long chain of black holes eating each other and getting bigger as they joined forces. These kinds of mergers typically impart large gravitational wave recoil kicks that can unbind the remnant from its host system. This could be overcome in a dense enough environment like a globular star cluster, where there could be lots of black holes, which could interact often with high escape velocities. It's a tempting idea, and it's a process that we do believe can happen, but in this case, there is a problem. You see, I told you that black holes are simple, they have mass, spin, and charge. Well, every time they merge they add their two masses together, but they also combine their spins. Since the spins are mostly in random directions, they tend to average out and mergers rarely yield daughter black holes with high spin magnitudes. The two black holes involved in this collision, however, were spinning at near the speed of light, making GW231123 not just the most massive, but also the fastest spinning black hole binary confidently detected with gravitational waves yet. So, some researchers concluded that something other than prior mergers must account for the tremendous masses of the progenitor black holes. The mystery continued. This is, until scientists at the Flatiron Institute Center for Computational Astrophysics came up with a new theory. The team, led by Othe Gottlieb, argue that the answer might lie in one of the most overlooked features of black hole formations, their parent star's magnetic fields. They created complex simulations for a 250 solar mass star and modeled its life from the moment it starts burning hydrogen to when it runs out and collapses in a supernova. The simulation showed that in fact the star would have burned through much of its mass as fuel by the time it collapsed, ending its life sitting at just 150 times the Sun's mass, now sitting just above that pesky mass gap. But the team still needed to work out what happened after that 150 solar mass object went bang. Did it match the high mass, fast-spinning black hole's LIGO saw? The team came up with a second set of much more complex simulations to study the aftermath of the supernova. They imagined the supernova's remnants as a black hole sitting at the center of a cloud of leftover stellar material laced with magnetic fields. First, they asked their simulation to imagine what would happen if the parent star had been non-rotating. As they expected, in this instance, the cloud of detritus fell into the black hole. Next, they asked the simulation to imagine that the parent star was spinning, and spinning fast. In this scenario, the cloud of dust formed a disk around a spinning black hole. As the disk accretes onto the black hole, it spins faster. This is where the magnetic fields come in. The team told the simulation to predict the outcome if the stellar dust cloud surrounding the newborn black hole was full of magnetic fields. In a similar way to what we see happening in active galactic nuclei forming quasars and blazars, the magnetic fields in the spinning disk were twisted up, exerting pressure of the debris and eventually, in some case, forming relativistic jets that blasted material away from the accretion disk, reducing the material available to feed the black hole. The stronger the magnetic fields, the greater this effect. In extreme cases with very strong magnetic fields, up to half of the star's original mass can be blasted away from the black hole. There was also another cool discovery to be found in the simulations. The team found that magnetically driven explosions could also impart what is called stochastic momentum to the black hole, likely resulting in a potentially significant natal kick compared to the unmagnetized direct collapse black hole. In other words, each time the magnetic fields generated an explosion of matter away from the region around the black hole, it sped up. If that kick was too powerful, it could unbind the binary pair, but just the right amount could spin the black hole faster without breaking the system. With the right spinning star and the right magnetic field, the team could produce a fast-spinning black hole that sits in the mass gap, just like those detected in signal GW231123. One of the exciting results of this work is that it suggests a connection between the mass of a black hole and how fast it spins. Strong magnetic fields can slow down a black hole and carry away some of the stellar mass, creating lighter and more slowly spinning black holes. Weaker fields allow heavier and faster spinning black holes. Unfortunately for now, astronomers know of no other black hole systems on which this connection can be observationally tested. However, future observations may find more such systems they could study to confirm this connection. The magnetic field-triggered explosions could generate short-lived, high-luminosity jets similar to very energetic gamma-ray bursts, and these might be observable. Looking for these gamma-ray signatures would help confirm Othe Gottlieb and his team's formation process and reveal how common these massive black holes might be in the universe. If the connection of mass and spin is confirmed as a fundamental pattern in black holes, it would help astronomers gain a deeper understanding of the fundamental physics of black holes. Just as exciting, this result would prove that the mass gap is fillable, meaning there may be plenty more intermediate mass black holes hiding out there in the darkness, waiting for us and our next generation of instruments to find them.